My name is Joe Clochon, and welcome to my video on the introduction to fire alarm systems. So I think we all have some basic familiarity with fire alarm systems. We've all been in gym class when maybe a basketball or something hits a pull station. This is a pull station. And or maybe, a smoke detector set off. And the horn strobes, these are horn strobes here. So the horn strobes all start going off, right? The strobes start flashing, the horns start sounding. The fire doors in the hallway will all close. The fire department shows up automatically. You probably don't notice, but the fans may shut down. But how does that work? I guess our goal is to figure out, how does the panel do that? When the fire department shows up, how do they know where to go? How do they know if the fire was in the gym or if it was in a mechanical room somewhere? How do they know? So there's two types of basic fire alarm systems. There's what's called conventional, which is generally the older kind, and then addressable or intelligent. And there's some difference in terminology between addressable and intelligent, but from my experience, the terms are basically interchangeable. So we're going to start with the more basic kind. We're going to start with the conventional panels. So down here I drew a little school building. Think of it, the most basic type of system you can have, right? So there's an east wing, a center wing, and a west wing. I drew a little panel here that has 3 zones, and there'd be a lot more stuff on a fire alarm panel. There'd be a power supply, there'd be the horn circuits, but these are all the initiating device circuits. You'll hear that term from time to time, IDC. Maybe I'll write it down. You probably won't be able to read it. IDC. And again, that stands for initiating device circuit. So this has 3 zones, and as you can probably tell, each zone is going to cover one area of the building. So let's imagine that this is a very basic school and there's 2 devices per wing. There's a pull station by the door and a smoke detector on the ceiling there. So let me try to draw the pull station. Bear with me. There's my box and my smoke detector. So, what's wrong here? Oh, wrong tool. Okay, so right now I'm drawing the wiring. So imagine that this red wire is the positive side of my circuit. It's going to go to the pull station. It's going to go out of the pull station to the smoke detector. And it's going to go up here for right now, and I'll explain that in a little bit. I'll use a different color for black because the wiring is almost always different. Same thing, the negative side of my circuit. It's going to come into this pull station, back out into the smoke detector, and then right up here. And again, we'll leave that for right now, excuse me. So, I should have labeled this. A lot of times in fire alarm prints, this would be labeled S for pull station. I don't think I have enough room here. SD for smoke detector. Good enough. So these are called normally open contact devices, and what that means is on this pull station internally, so you have a wire coming into one side and a wire coming into the other side, and these wires are not touching internally. The pull station does not draw any current. The circuit is not being passed through this pull station. It just goes right back out the other side. That's a normally open device. So what that means is the circuit doesn't even really know it's there for right now. If it's in a normal state, meaning it hasn't just been pulled by somebody, the circuit just goes into and out of it. It's kind of like a light switch that isn't on. It's not doing anything at this point. So this circuit goes into the pull station, right back out of it, into the smoke detector, right back out of it on both sides. And at the very end of this circuit, there's a resistor. Hopefully you're at least a little familiar with what a resistor is. But it's the panel's method. This is a symbol for resistor. This is not going to turn out well. It's actually a little better than I thought. The panel is designed to always be drawing a certain amount of current. So in a normal state, the current would be flowing through the negative side here. It's not going through the pull station like we just talked about because it's normally open, right? It's not shorted. This isn't passing through. it goes out. Smoke detector is the same way. The smoke detector will draw a little bit of current, but it's very minimal and the panel can't even really tell it's there. And then it goes through this end-of-line resistor, and this is drawing some current. Hopefully at some point we'll probably get into Ohm's law, but hopefully you're at least a little bit familiar with the idea that if you have a circuit that has, well, these are typically 24 volts. So let's say this is 24 volts, and it's DC, but we'll get into that in another video. It's 24 volts DC. If you have resistance, that affects the current. So the voltage, current, and resistance are all affected by each other. And like I said, we'll get into that a little bit more in the future. But for right now, the panel knows how much resistance or how much current should be drawn in a normal state. So the circuit's going out. It's not going through the pull station. It's not going through the smoke detector, well, at least for the most part. And it's going through this resistor and back. So it's a complete circuit, and the panel's happy because it sees its resistor, and that's what it should have. That's the normal amount of voltage. The panel's not an alarm, and it's not in trouble. This little yellow light represents trouble, and that's kind of what I want to get into right now. So let's say, what's the purpose of this resistor? Why do we need that? Well, what would happen if I cut a wire right here? So let's say I open up this circuit. Now it's not a complete circuit, right? It's not going through this resistor. So the panel, it's no longer a complete circuit. It can no longer see this resistor. So now there's no current being drawn in that system, in that circuit. The panel's going to go into trouble. This little yellow light here indicates trouble. So this would be lit up yellow right now. This circuit is not complete. It does not see its resistor. It goes into trouble. That's the way of, the resistor always has to be at the very end of the circuit, and that's the way that the panel knows the circuit is okay. If I put this resistor right here, the panel wouldn't really care what happened beyond that as far as opens and stuff go. If I could cut the wiring all I want, the panel just sees its resistor and is happy. So right now, when this is a complete circuit, I don't remember what color I was using. I think this gray, hopefully. So, assuming this circuit's complete, no, I don't think that's right, whatever. Assuming that circuit's complete, it sees the resistor, it's happy. So that's a normal circuit, that's a normal condition. Panel would be clear. Now let's say somebody walked up and pulled this pull station right here. Well, now it's just kind of like turning on a light switch. It's going to short. So if this were the positive side of the circuit, this is my pull station, and this is negative. Once you walk up and pull it and activate it, it shorts. The contacts close. So now your circuit goes through the pull station. It's shorted. It goes right through the positive side. So this panel, the current would increase. The current goes up infinitely, really, except for the engineering in here. It's designed to withhold a short. If this were a normal power supply, or maybe think of your wiring in your house. Your wiring in your house is a little bit different because it's not DC. It's not direct current. It's alternating current. And we'll get into that in the future. But there'd be some sort of circuit protection, like a fuse or a circuit breaker that would pop once the current went up too much, because when you have a short circuit, the current goes up infinitely because there's literally no resistance in the system except for the minimal resistance of the wiring itself. So the fire alarm panels are designed to detect a short. So an alarm shorts out a circuit, and that's how the panel knows it's an alarm. So if somebody walked up, pulled this pull station, the current on this circuit goes up, and the panel knows it's an alarm. So this light would turn on red, and you'd probably have some label that said, first floor east. So when the fire department showed up, they would at least know. They might not know exactly what room it's in, but if this were a bigger school, but they'd at least know where to start, give them some direction. So just as a quick review, I don't want to make this first video too long. We'll get into more detail in the next videos, but in a normal circumstance, you'd have a panel that would be putting out usually 24 volts DC. You have a bunch of normally open devices, which means devices that aren't really passing any current through them, but once they're activated, they short. So the circuit would go, to the pull station, but not really through it, to the smoke detector, not really through it, and through this end-of-line resistor. And this end-of-line resistor is what the panel sees, and it's what draws the proper amount of current so that the panel is in a normal state. If anything were activated, this pull station or this smoke detector, the current would increase and the panel would go into alarm. And again, however specific you need to be for the fire department, if you needed a different zone for every room, or if they wanted to know exactly what room in alarm we're in. If you had a conventional panel like this, and we'll get into addressable panels in the future, but if you had a conventional panel like this, you would need a separate zone, a separate physical circuit for every room. You know, you'd need maybe 100 zones if you had a big enough building. So that was one of the limitations of this older style conventional panel. But again, I think that's about where I want to stop for right now. We'll get into a little bit more detail in the next video.